Okay, thanks for the introduction. So today, Robert I. Booth is going to be talking about engineering CSS surgery, implementing any CNOT in any code.
Thank you, thank you. Yeah, this is a bit of an interesting project. It started with Clément coming to Edinburgh to do an internship with Joschka as a master's student. And he was sitting in the same office with me. I hadn't really thought about anything related to quantum error correction, or at least not in anything more than very superficial levels. And he had this project with Joschka on sort of trying to generalize CSS surgery, or sorry, to generalize lattice surgery in various ways. And he became interested in a paper from a few years ago by people from the community here, Alexander Cowtan and Simon Burton, where they came up with the notion of lattice surgery for CSS codes. And that paper is sort of entirely stated in the language of category theory and a bit of homological algebra. And so Clément was asking me questions about category theory and a bit about homological algebra. And sort of over the course of a few months, these questions started adding up more and more, and I sort of got invested more and more into this project. And I basically ended up supervising it to a pretty big degree. And sort of ended up with this paper on CSS surgery that I'm quite happy with. Now, to give a little bit of context to this paper, at least in the way I recontextualized it for myself after having done it, I think this paper fits into, or is like maybe a very small part of a, say, bigger framework or push that I think needs to happen in quantum error correction or fault-tolerant compilation. That is, that if I want to take a quantum program and pass it to a compiler, some logical program that someone has come up with, and I actually want to run it on a Python computer, and I need to compile it to fault-tolerant implementation, whatever that means on a given hardware. And this compiler needs to be able to do a handful of different things. I think it needs to be able to map between different representations of quantum operations that appear in the literature, and also throughout different compilation techniques that appear in the literature. It also needs to be able to correctly compile to different hardwares without hopefully having to tailor the entire compiler for a specific hardware. And ideally, although that's really not the topic of this talk, you would also be able to perform optimizations on the resulting instruction sets while preserving fault tolerance. And so there's, I think, a need to develop a framework and sort of representations for quantum programs as they undergo different sort of subsequent compiler passes that give you a sufficient level of abstraction to reason your way through things in a systematic or principled way. And so I think that's really where this paper fits into the picture, is that it's sort of a very abstract way of thinking about lattice surgery that I think gives a nice, at least maybe, if not the actual intermediate representation that you will want to use in a compiler, at least insight into the type of thing that can work. Now, it's all based on the symplectic representation, apparently, of the Pauli group. So if you recall, I'm sure you all know, the Pauli group is generated by the Pauli X, Y, Z operators. And we can, to any Pauli string, if we ignore the global phase, so the phase of the Pauli, associate it to a pair of binary characters that each represent the X weight and the Z weight of the Pauli. And more generally, if I look at the Pauli group on n qubits, then I can represent it as a pair of strings of length n over the binary field f2, or I guess one string. of length 2. Now, the nice thing about this representation is that you can compute the commutation relation between Pauli operators purely in terms of this representation. So here I've got sort of taking two Paulis represented like this, then I get this phase as a function of AD minus BC, which I can compute just from the binary strings in my representation, or my presentation, I suppose. And then these Paulis are going to commute if and only if this this quantity AD minus BC is equal to 0. More generally, if you sort of lift this to this right-hand side string of Paulis, then it's fairly straightforward to show that two Paulis will commute if and only if. So two Paulis represented by the vectors AB on the left here. I think I can draw like this. AB on the left here and CD on the right will commute if and only if this matricial equation holds. But this is really just sort of like a rephrasing of this to each, so sort of to each pair of Paulis acting on each qubit, or I guess, yeah, on each qubit. And this equation at the bottom has a symplectic structure, this matrix that allows us to compute this quantity is called a symplectic form. And this sort of symplectic form gives its name to this whole presentation, hence the symplectic presentation of the Pauli group. Now, in quantum error correction, we're interested in encoding states into, or more generally, spaces into, or sorry, more generally, qubits into a bigger set of qubits into a larger Hilbert space with some degree of symmetry in order to be able to detect errors when the symmetry of the overall system is broken. And the way, the sort of standard way of doing this is through the stabilizer theory, which I guess probably most of you are quite familiar with, so I'll just go through it quite quickly in order to introduce notation. And the idea in the stabilizer theory is that I have some state psi, which is stabilized by an abelian subgroup of the Pauli operators, that is, applying any element of that subgroup to x to psi, sorry, use it invariant. And in this symplectic presentation of the Pauli group, I can actually recover the stabilizer group or a definition, like so an equivalent presentation of stabilizer groups fairly straightforwardly. That is, if I take some, I draw generating sets, so some generating, this is very awkward. You get a very awkward angle of me. A generating set of the stabilizer group and look at the corresponding binary vectors in the symplectic presentation. Then assembling these into a matrix yields the parity check matrix associated with that code. And this parity check matrix is going to be, and a matrix H is going to be a parity check matrix exactly when this equation holds with respect to the symplectic form. But once again, this is just a rephrasing of this equation here to each of the generators of the stabilizer group. Cool. And then to sort of, in some sense, this is a specific choice of generating set for the stabilizer group, but I can recover just the stabilizer group by looking at the kernel of this parity check matrix, which is going to correspond exactly to sort of all of the elements that commute. Have I done this right? No, I've got this slightly wrong. I think here it should be the image of the transpose of the parity check matrix, which is going to be sort of all of the elements of the Pauli group that I can generate from my specific set of generators, or the entire stabilizer group. My slides are a bit too big. Oops. Now, one more thing that we can quite nicely recover from this presentation of the stabilizer group is the set of logical operators, which I can recover in the following form. I take the kernel of this product matrix H times the symplectic matrix, and this describes sort of following. Actually, maybe I've done this slightly wrong. Should be a transpose here. This right? No, I think this is right. This is going to give me exactly the set of Pauli operators that commute with all of the elements of the stabilizer group. And then quotienting that by the image of H transpose, which is specific exactly the stabilizers. This is what should be here. Image of H transpose. Sort of quotients by the things that leave my state invariant. So in essence, what this quotient is doing is it's taking those Pauli operators that leave the code space invariant, and then quotienting within it's taking those Pauli operators that preserve the code itself, and then quotienting by the Paulis that leave the code space invariant, which is precisely the set of Paulis that are going to have a logical effect on the encoded state in my stabilizer group. Okay, so CSS codes are a specific family of stabilizer codes that have a simple structure. I've got extra slides. And the idea is that this should be not 1 but H. That I can split my parity check matrix H into these two gradings here, which are going to be correspond just to Pauli X operators on the top row and just to Pauli Z operators on the bottom row. Have I done this right? Yeah. And as a result, I have generators of my stabilizer group that are either just written in terms of X operators or generators that are just written in terms of Z operators. And I can represent this graphically by the Tanner graph on the left, where the rows corresponding to X operators are drawn above, and they're connected to qubits, which are these dots in the middle, precisely when I have a 1 in the corresponding row, or the parity check is applying to that qubit, and sort of correspondingly for the Z operators below. So I have this nice sort of bipartite or maybe tripartite representation of CSS codes that is very convenient when reasoning about CSS codes. Now, that's sort of the first part of the title, CSS surgery. The second part of the title, lattice surgery, is a technique that was originally developed, I think, by Dominic Horstman for implementing CNOT gates in instances of what's known as the surface code. Now, the surface code is a specific example of a CSS code. And the idea is that at the logical level, that is the actual operation that I implement on my encoded qubits, I want to perform a CNOT, and I'm going to try and do that by decomposing it into in the following way. I add an additional auxiliary qubit in the plus state. I perform a projection onto the +1 eigenstate of ZZ on the first two qubits, and then this one should be XX. I've got two lazy copy pasting things on the bottom two qubits and sort of measure out my auxiliary qubit. And this implements a CNOT, and it's quite easy to see that, I did this in the wrong order. It's quite easy to see that this does indeed implement a CNOT operation for those of us who are familiar with ZX, because these projections in ZX take the following form, and sort of similarly, I guess, for the plus state and zero effect are corresponding units and co-units of the right colors. And so the challenge of surgery is then to implement these logical operations corresponding to these phaseless spiders at the level of codes. That is, I want to implement a physical operation on my codes that at the logical operation has this corresponding effect. And the way that this is done is that we decompose these spiders yet again into these 2-to-1 and 1-to-2 elementary spiders, and we try and implement these things. And these things all have names in terms of merges and splits. Annoyingly, there's a bit of a confusion in terms of the convention of which is an X and which is a Z split, depending on whether you are from the ZX calculus community and you think that green spiders are all Zs and red spiders are all X, or if you're from the say more quantum error correction community where you are interested in things that preserve the X or Z grading respectively. I've chosen to take the latter convention because that's the one that CNOT took in the article. Now, the point is we now want to individually come up with methods for implementing each of these operations at the level of codes. The sort of natural way to try and go about this is to say, well, here I'm doing a thing that takes 2 qubits to 1 qubit. And so at the level of the codes, I might try and think of this as saying, I have an instance of a qubit here encoded in some CSS code. Similarly, I have another instance of a CSS code encoding a qubit below, or a surface code. And I want to somehow merge them into one big surface code patch in order to implement this merge and end up with sort of 1 qubit encoded in one large surface code patch. Now, what does this look like in terms of tanagraphs? So these are the tanagraphs for 2 small instances of the surface code, each of which encodes a single qubit. And I can do this kind of merging operation essentially by gluing along each of my edges at the level of the qubits themselves. I'm essentially just going to be doing 2-to-1 spiders of the corresponding color to each of these qubits here, where I have a red line between them. And this is going to glue both patches of my surface code together, and I'm going to end up with one big surface code patch that has essentially implemented this merging operation. And if you sort of check, there's sort of a number of articles out there. The original one, I think there's one by Dominic, and there's a more recent one by Alex Kissinger about doing this in ZX calculus, proving that doing this Z merge does indeed implement the right thing on the logical qubits. But so now the question becomes, I have this more general notion of CSS codes, and I have this example of surgery that works in the case of the surface code. How do I go about applying this kind of idea, but to these more general CSS codes? And you can sort of try and generalize this idea of gluing graphs together at the level of tanagraphs, and you can sort of muddle your way through, well, maybe not muddle, but you can come up with this notion of gluing tanagraphs such that, for instance, if I take one slightly larger patch, surface code patch, and I can glue it to itself along edges, and I end up with a sort of cylinder code. And then if you want doing that step once again along the opposite boundaries, I would end up with some kind of torus. But this kind of this idea of gluing graphs has some problems. For instance, if I'm not careful about how I allow myself to glue my graphs together, then it's totally possible to glue 2 graphs together in a way that produces a new Tanner graph that is not actually the Tanner graph associated to any valid CSS code. For instance, here, if I glue these two qubits on the left, then I end up with parity checks that no longer commute, and therefore I'm not even in a valid stabilizer code anymore. Yeah, sorry. And the other sort of aspect that's a little more tricky to I can't really draw drawings very conveniently for is that Tanner graphs implicitly forget the linear or the group structure of stabilizer groups. That is, if I take two generators of my stabilizer group and multiply them, or I guess in the symplectic presentation, add them, this also gives me a new element of the stabilizer group, but these don't typically appear in the Tanner graphs. And this is actually quite important because they give you an additional degree of flexibility in the ways that you might glue things together that is just not apparent at the level of Tanner graphs. So the question is, where do we go from here? How do we replace Tanner graphs with something that is more convenient? Are there any questions up until this point about what I've talked about? I guess it's been pretty general, but before I move on to into the more technical stuff. No? Brilliant. So the idea that allows us to move forward, which is not our idea, it's appeared in various forms in the quantum error correction literature, sort of originally not in the setting of CSS codes, I think, but in the setting of topological codes. I think they were using chain complexes maybe in a slightly different way. And then in this paper by Alex and Simon, they pointed out that CSS codes themselves can be rephrased in this language of homological algebra. Now, how does that work? Well, the point is that if I return to this sort of defining property of CSS codes here, this form that the parity check matrix must take, and this defining equation for stabilizer groups, and sort of substitute my parity check matrix in for H here and here, then I end up with this equation here, which is equivalent to asking that the sort of submatrix that describes the Z stabilizers multiplied by the transpose of the X stabilizers is equal to 0. And if you're a mathematician or you work on these kinds of things, then you'll recognize that this gives you a sort of very simple form of a chain complex in the following form, where I just sort of line up Px and Pz, and this sequence of linear maps is a chain complex exactly when they multiply to 0, as we've just proved is the case for CSS codes. So we can essentially always think about CSS codes as chain complexes of length 2. There's sort of a more general notion of chain complexes that are longer, but we're only going to be interested in these length 2 chain complexes, where there are 2 linear maps. Now,
sorry, I have a question.
Yes, go for it.
So you have this symplectic condition of a stabilizer group. Why wouldn't you just get PZ PX transpose is equal to PX PZ transpose?
Someone asked me this question at the last talk I gave, and I couldn't remember, and they gave me the answer, and I still can't remember. There's some elementary manipulation that you can do to show that this is equal to the thing on the right. How do you do that? I can't remember. I could probably figure this out if I had 2 or 3 minutes, but I don't really want to break here to do it. But the thing on the right follows from the thing on the left. This is also a plus in the case of thing. I'll come back to this at the end for you, Sarah. I don't want to sit down and have to think about it and lose the flow of the presentation.
Thanks.
Sorry. I should prepare this because I get this talk I've had this question 3 times and I keep forgetting how it works, but whatever. Now, why would I be interested in representing my CSS codes in this way? Well, the point is that now operations that preserve the structure of the CSS codes are sort of naturally represented in this language of chain complexes or homological algebra. The point is that these operations that preserve the structure of CSS codes are what is known as chain maps in homological algebra. And they take the following form. So I have a first code, which is my CSS code, represented. So the number that's going by. I have a first CSS code represented as a chain complex that is going to be the domain of my CSS operation, and then a second CSS code as the codomain. And a CSS operation is specified by a choice of these 3 maps A, B, and C that have to verify a sequence of properties. The map B is essentially the map that acts on the physical Hilbert space. This is the map that I will implement on my physical qubits as part of this, to implement the CSS operation. So this is the physical map. And then these 2 maps, A and C, on the left and right, enforce conditions on the X stabilizers and Z parity checks, or at least how these things are mapped between my 2 CSS codes. So the map A enforces that the X stabilizers in my original code are mapped to still X stabilizers in my codomain. And similarly, the sort of right-hand linear map C enforces that Z checks are mapped to Z checks in the resulting code. And this is essentially exactly what you need in order for your linear operation B, or physical operation B acting on the Hilbert space to preserve these gradings between the grading of the X operators and the splitting, I guess, of the X from the Z operators when I implement it. Now, I can draw the physical operation, the physical map, as a scalable ZX diagram. And the idea is that I now have, say, morphisms here from n prime qubits. I implement this physical map B on my physical qubits. And then I also implement the projector onto the stabilizers of the X stabilizers of the new code. The point is that because I don't impose any properties on this matrix A, in principle, this map allows me to, this sort of new choice of Px prime allows me to add new X stabilizers essentially for free. Therefore, I need to make sure that the state of my system is always a valid state of the stabilizer code of the code space. Hence the projection onto the X operator, the X stabilizers. Cool. Now we can say quite a lot more about this homological framework. Firstly, there is this natural operation that appears throughout homological algebra, and it basically gives its name to the entire field, which is this construction called the homology. So if I take some chain complex here and I apply the following operation, that is, I take the image of the this matrix PX transpose, which are precisely the have I done this right? Yes. These are going to be precisely the set of operations that commute with all of the Z operators, the Z stabilizers of my stabilizer group, and quotient by the Z stabilizers. I've done this wrong again. This is annoying. This should be, sorry, this should be, I thought I fixed this, but I guess I didn't hit save. This should be kernel of PZ quotiented by the image of PX transpose. We're just saying, if I take the set of all operators, of all Z operators that commute, sorry, all X operators that commute with all of the Z parity checks, and then quotient that by the set of X stabilizers, I get exactly the set of logical Pauli X operators. And similarly, there's a sort of analogous construction that is called the cohomology that is going to give me the logical Pauli Zs. I guess I fix it on this slide, but not the previous slide. I see. So here, these equations are correct. So the top ones give me the logical Pauli Zs. No, the logical, I forgot. The top one gave me the logical Pauli X's, and the bottom one gave me the logical Pauli Zs. This is essentially just a reformulation of this equation we had a few slides ago that said that the logical operators were given by something of this form, right? Specified to the case of CSS codes where my parity check matrix splits into these submatrices PX and PZs. Now, in fact, I can also, from my CSS operation in a natural way, determine what the corresponding logical effect of that CSS operation is at the level of the logical Paulis. And that is because, in fact, the homology is not just defined on chain complexes. It is functorial as a map from the category essentially of chain complexes and chain maps, or in our case, CSS codes and CSS operations, down to the logical Paulis and the sort of logical maps between those. And this is, in some sense, is the cornerstone of this homological approach to CSS codes in general, and in our case, specifically to lattice surgery. It's how we're going to build our CSS surgery framework. Now, there's one caveat with this construction, and that is that these homologies here and here do not come equipped with a canonical choice of basis. When you take the homology, you lose this choice of basis. And this is not at all a benign thing. In fact, different choices of bases are going to have completely different fault tolerance properties. And in some sense, it's not maybe surprising that this is the case, because a choice of basis amounts to a choice of encoder for your code. This homology operation gives us the logical map as a abstract linear map, but it doesn't actually describe what elements of the homologies are which Paulis, and therefore how the logical operation acts in that. However, if we choose a specific basis for each of H of C and H of D, and M is the matrix representation of M is the matrix representation of the homology, the homological map in that choice of basis, and here EC and ED are the corresponding encoders corresponding to those choice of bases, then we get the following equation, which is essentially saying if I do this physical operation on my physical qubits, then at the logical level, I do indeed get this matrix representation this matrix M acting on my logical qubits. Cool. Are there any questions about this? This is a good place to take a break.
Yeah, I have a question about the fault-tolerant properties.
Give me 10 minutes.
Oh, okay.
I'll get there.
Okay, great.
Oh, I guess, I mean, well, okay, unless it's a specific question about this.
Yeah, like I found this term a bit vague. Like, are you referring to transversal gates? Like, what kind of properties are you thinking about?
I mean, essentially every fault-tolerant property that you can think of probably falls within this, in the sense that even if you have, say, trivial codes with the identity encoder as your sort of starting point, you can apply any family of CNOTs between any qubits and end up with a still sort of essentially an encoder for the same code, but now it spreads errors everywhere. And you have no hope of having any kind of fault tolerance. So in some sense, like every fault tolerant property in some way relies on either a choice of encoder or at the very least a choice of like what binary strings represent which Pauli operators at the physical level.
And different in the sense that different properties in the sense that you will have different Pauli propagation.
Yes, because you can always say for a given choice of encoder EC here, post-compose that by an arbitrary unitary here, and you'll get another encoder for the same code. But sorry, have I done this right? No. You can, have I got this right? You can, I mean, in general, I guess you can always put CNOTs in various ways on your qubits here and get encoders for essentially the same code as a result, and these will spread errors in very different ways. I guess more specifically, you can do an arbitrary unitary here, and this will correspond to some unitary on the other end here, and depending on what unitary that is, you will have different. It realistically will probably spread errors. So this choice of encoder does matter for the fault tolerance of your code.
Thank you.
I also have a question. I'm just kind of to bring it back to the example that you started with in the beginning. What would be the homological map of like a split or merge in the surface code? Just to make it very concrete.
I mean, in the case of a surface code, it's going to be, where am I? And do I have a slide where it's easy to draw here? I will essentially here have a direct sum of two surface code patches. So I don't want to draw it, but like, and then my middle map is going to be essentially the merge applied. I mean, it's a bit of a pain to draw, but it's going to correspond to the linear map that I get from doing like a something like this across each of these pairs of qubits. So I guess it will be something like where am I? Here will be something like it will be a bunch of mergers applied to each of these, and then similarly, I'm going to glue the corresponding X operators. It's too many slides to go back and forth between. Similarly, I will glue each of these guys, and then I will be the identity on everything else. Does that make sense?
Yeah.
Cool.
Thanks.
Cool. The logical map tree, blah, 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 blah. Okay, so how do we now use this this homological framework to come up with surgery procedures? So the definition that essentially Clément came up with, which is actually quite natural, is the following one. So in order to describe a surgery operation on a sort of code C that I want to apply the surgery to, the data that I need to give of this in order to implement this surgery is the data of a subcode. That is, I take another CSS code S, or in this case a chain complex that injectively embeds into C. So it's sort of a sub-object in a categorical sense. And then I perform a quotient by this subcode. And sort of, I guess mathematically, this is a fairly natural thing to ask for a couple of reasons. The first is that, in some sense, quotienting corresponds to gluing things in sort of a categorical sense, I suppose. In Alex and Simon's original article, they had a notion that was in terms of push-outs, but you can actually reformulate that notion fairly straightforwardly into this one. And this one has a couple of advantages. The first one is that, for me, I think it's a bit more natural to talk about mergers internal to a single code in this language. And secondly, a more mathematical advantage is that this sequence of maps actually forms what is called a short exact sequence, which I'm not going to bother defining because it's mathematical and maybe not that interesting, and sort of textbook thing in algebraic topology. But the interesting point is maybe not that this thing forms a short exact sequence, but maybe more that when you have a short exact sequence, you can apply a standard result of algebraic topology to get a long exact sequence on the homology of the corresponding chain complexes in the sequence. And what's of interest to us now is that if I look at this, I got this long sequence of 9 chain complex, or 9 homologies, but in the middle of this long exact sequence, this map that I've outlined in red is exactly the logical operation that is implemented by my merge. And so I can use the properties of this long exact sequence to reason my way through my surgery procedure. In particular, I can use, in some ways, the properties of the maps that lie on either side of this logical operation, along with the sort of defining properties of exact sequences in order to control my logical operations. I didn't really feel like I would have the time to go into this in great detail, but I think the point to note here is that this is in some sense the natural, I don't want to say conclusion because there's more to do maybe, but maybe the first natural conclusion that follows from the reformulation of CSS codes and CSS surgery in particular into the language of homological algebra. And in some sense, I feel like it's a bit of a shame that this wasn't in Alex and Simon's original article, because I think if you ask people that work with homological algebra a lot, this is maybe the first thing that they would think to do. And it's sort of a very convenient way to think about this logical operation. It leads to the construction that I'm about to tell you about. Now, there's one complication, and sort of why I don't really want to go into a lot of the details, is that in order to make all of this stuff work, we have to go back to this problem here that everything has to be done with respect to some choice of basis for the homology. And so even once we have extracted this long exact sequence on homology, we have to be very careful about constructing bases for these things in a way that the resulting maps have quote unquote nice representations that have, say, good fault tolerance properties or sort of have natural representations that are easy to work with. If you want to find out about that, I'm going to point you towards the article because it's sort of quite long and sort of technical without being particularly deep, I would say. It's just sort of carefully constructing bases in such a way that things work out. But the point is that doing this, Clément was able to come up with these physical maps, which are these things on the left that do in fact represent or implement these X and Z merges and splits on an arbitrary CSS code. So you can have a CSS code that encodes multiple qubits, and you just want to do a CNOT internal to that code. This will allow you to do it. Or you can take two disjoint CSS codes, take their direct sum, and apply the same methodology. The point being, you're implementing the right projections and leaving the remaining qubits invariant when you apply these operations. Now, an important question, I think, whenever you're doing something like lattice surgery, where the point is to act on encoded data, is how fault tolerant are the resulting operations? This is actually a really tricky question to answer. Firstly, because as far as I can tell, in the literature, there's not particularly a clear, say, conceptual framework for thinking about fault tolerance in these general scenarios. A lot of the time, you either have to produce a specific circuit and look at that specific circuit in order to determine whether it has good fault-tolerant properties or not. And at the level of generality where we work, where we've sort of abstracted away completely from the circuit picture, it's tricky to make these arguments, at least at the full level of generality where you're working at. Now, we can say a couple of things. Firstly, Clément was able to prove that if you have a code and you put these up, you do this surgery procedure on it, then pre-existing Pauli errors on your physical qubits are not going to propagate catastrophically. So the point is Paulis that appear before your physical operations are not going to propagate. Well, okay, so they're going to propagate. Maybe this shouldn't say Paulis here do not propagate here, but sort of do not propagate catastrophically. So morally on the right, you'll have exactly the same number of Pauli errors as what you had on the left. And similarly for the sort of X, Z, sort of the flipped color projection. And then on a very case-by-case basis, you can choose subcodes in such a way that they guarantee only local interactions when you perform the merges and the splits. So the point being that when I do, if I've chosen my subcodes well enough, then these linear maps, or these sort of SZX arrows, remain local. The overall effect of these remains local, and therefore doesn't propagate errors. And if furthermore the codes are LDPC, then this projection is also essentially sparse and is not going to propagate errors catastrophically. And this means that the fault tolerance properties in this specific case are much stronger. For instance, internal errors are also not going to propagate too far for sort of given implementations that we described. Now, the problem with this is that for now, at least, it's very much on a case-by-case basis. Clément gave an example in the paper. He has some other ones, I think, in notes of where this works. But it involves looking at a specific instance of the code and then constructing specific bases for that do a good job. And we don't really have a general way of doing this for arbitrary choices of code. Although I'd be very interested to see if there is, for instance, an algorithm that will give you this kind of thing. Cool. So the takeaway for me from this paper is that homological algebra seems to provide the computational tools to reason about CSS operations between CSS codes. That is, it gives you methods with which you can actually practically compute things or properties of these CSS operations in a way that in sort of other approaches to CSS surgery, the computations are, I think, much more ad hoc and sort of trickier to carry out. Although I haven't talked about it here, I think an interesting aspect of the work is that actually it offers the promise of compiling entire circuits of CNOTs. That is, instead of just doing a single CNOT with lattice surgery, I do a whole circuit of CNOTs. Now, we didn't do this for a couple of reasons. The first one is that circuits of CNOTs are perhaps not that interesting by themselves. And the second one is that these arguments of fault tolerance become even more complicated in the case of circuits of CNOTs, and since we only have these sort of case-by-case examples, it just seemed a bit out of reach to come up with examples of big circuits of CNOTs that were implementable fault-tolerantly using lattice surgery. But I think this is still an exciting thing, at least in principle, from the perspective of fault-tolerant compilation. Oh, I put these. So I'm just going to leave you with, there's a couple of limitations, I guess, for the overall framework. The first one, obviously, is that we can only do CNOTs, which are by themselves not a particularly interesting fragment of, say, quantum computation. We can't even do Clifford circuits in this language. If we could do Clifford circuits, I think it would be quite interesting, because then with magic state distillation, you will be able to do quite a lot more. And then the fault tolerance arguments are still pretty ad hoc, even if I think there's some promising suggestive results. It's still not sort of to a level of satisfaction. So I'm still not fully satisfied with it. So I'm going to leave you with this question, which is it possible to come up with a framework for compiling, say, Clifford circuits and reasoning about fault tolerance in a more principled way in order to generalize some of these results, like lattice surgery to the case of Clifford circuits, while maintaining sort of a good handle on the fault tolerance of the resulting implementation? I think such a thing would be incredibly useful for designing, say, a quantum compiler for fault-tolerant implementations. Yeah, so I think that's basically everything I wanted to say. Yeah.
Thank you, Robert. Questions? I have a question.
Yeah.
So are you like working in the category of like short exact sequences over matrices over
the category of chain complexes, I guess?
But you're only using the like ones with two
length 2. Yeah, I guess it's like the subcategory of those of length 2.
And then you're working with short exact sequences over short.
Oh, I guess, yeah. I guess so. Yeah.
So one thing that Simon and Alex do is like they take the tensor product of these chain complexes as short exact sequences to talk about like I forget exactly what they do, but they like when you take the tensor product of two chain complexes as short exact sequences, then you get a longer short exact sequence.
Yeah, so there's
version with
I guess the point. So I'm not sure if this is exactly what's in that paper because I can't remember what is in which paper in which formulation. But there's this thing called the hypergraph product of chain complexes that takes two chain complexes that represent classical codes and constructs a sort of big quantum code out of those two. And in some sense, I need to go back a lot of slides, I guess. It gives you a generalization of a surface code where you have sort of an instance of one classical code here and an instance of a second classical code here. The hypergraph product somehow like builds all of these sort of two-dimensional structure of the quantum code. If you take the repetition code for both these codes, you end up with the surface code. And if you take other more interesting examples, you get more interesting things. Is that what you're talking about?
I guess the general question is why do you work only with short exact sequences, and how does that like?
You mean not longer ones?
Yeah, or not like these more general chain complexes that they have in.
So, I mean, if you take more general chain complexes, the point is that the additional degrees don't actually do anything to describe anything at the level of quantum error correction. They just describe additional redundancy on the classical data that you get out of your quantum measurements when you run the error correction. So I guess like there's some interest in that, in that it does allow you to describe that classical redundancy, but it doesn't really give you any more flexibility in talking about CSS codes.
Okay. Question from Oxford.
What's that?
It's a question from Oxford, I think.
Ah.
Oh yeah, I had a very similar question to Cole. So, like when we go from the short exact sequence to the non-exact sequence, we don't have enough. Like we only have so many maps, right, in our chain.
Yeah.
Like the non-exact sequence is actually only like 4 steps long, right?
Yeah. I mean, I drew the whole thing just because I was talking about the general result, but I guess here, like the gray stuff is basically trivial.
Okay.
In this, because the sort of, I guess what on one end it would just be the whole spaces, and on the other end it will be trivial. I can't remember which way.
Yeah, but so like I'm trying to understand like what about quantum error correction makes it so that the chain complexes are exactly 2 steps long, you know, like
I mean, I don't know if there's a specific, like a particularly deep reason beyond this thing here. The fact that you can represent them as chain complexes at all comes down to the fact that you can split things into these two gradings. And I don't really know I don't think that there's a sort of much more profound reason than this.
okay, thank you.
Sarah.
Thank you for the talk. I wonder, so actually, Cole asked a question that I was wondering. It seems that your method could really be applied to find the hypergraph product codes because like you're basically taking two linear codes that is of really good properties. But what I was wondering is if you go back to your slides where you have this like 3 rows of chains and you have this mapping from
this one.
No, like later, like you have this like gray.
Oh, this thing here.
Yeah, like is it trivial to find these maps? Like for example, the blue one, between H1S0 to H1C0, is it easy to know how do you map from one to the other?
It's not extremely difficult, but you get only, like I said, you only get it as a linear map. So it is defined essentially by a universal property, and it's not too hard to understand how that gives you a linear map on the quotient spaces that are involved here, because it has like a bunch of commutation relations that it has to respect. But once again, when you choose a basis, this red arrow, which is the one we're interested in, can take basically completely different forms depending on whether you've chosen your basis well or not.
So concretely, can I think of a map as being mapping stabilizers to another stabilizers, and both stabilizers acting on the same number of qubits?
Which one? You mean the red map in the middle here?
Yeah. Or like
No, you should think of it maybe more as it is a map. I mean, in some sense, I guess you can think of it as a map on the physical space that respects the quotienting when you take the homology, that is the map down to the logical operators, and then pushing through those quotienting operations, you get an actual map on the vector spaces of logical operations. But in principle, like this vector space, I'm not drawing for some reason. This vector space here and this vector space here have different dimensions in principle, because you're quotienting on the right. So you can reduce the number of logicals, but in fact you can also, in some somewhat maybe confusing fashion, increase the number of logicals through this quotienting. This is, for instance, what would happen if you were to go back to here. If I were to merge sort of along these boundaries, again, I get a torus, which encodes, I think, 2 qubits instead of just 1 at that point.
Oh, so that's why when you specify the vector spaces between the chain complexes, you use x and x prime to denote different dimensions.
Yeah.
Okay. And sorry, I'm maybe missing the context here, but how has this chain complexes allow you to investigate the fault-tolerant properties of a code? Overview, sorry.
I guess it doesn't allow you to see the fault-tolerant properties themselves, and that's sort of what I'm getting at with the question I was leaving at the end, is that you sort of have to do this work and then sort of on the side worry about the fault tolerance and like how that impacts the choices that you're making when you're constructing these maps, which is not, I think, ideal.
Okay.
So yeah, because once again, like the fault tolerance properties depend on the choice of bases that you make for the homologies H1, like on both sides of this logical map.
So suppose you're given 2 subcodes. Are you able to construct a hypergraph protocols and say explicitly what do you expect in terms of the error propagation?
So I'm not sure I fully understand. Are you saying if I were to take 2 CSS codes and corresponding, or if I were to take 2 codes and corresponding subcodes, and then take the hypergraph product of the codes and the subcodes, which I assume it still embeds into the hypergraph product of the ambient codes, does that help with the fault tolerance? Is that the question?
Or do you know what would be the fault-tolerant properties of the newly composed codes?
I haven't thought about it at all. Yeah, I'm not sure. I guess you have quite a lot of control on the homology of hypergraph product codes, because it splits in a nice way, if I remember correctly. So maybe, but like I said, I haven't really thought about it.
Thank you.
I have a final question.
Yeah.
So this this diagram on top, if I understand correctly, this is a chain complex of chain complexes.
Yeah.
More specifically, a short exact sequence of short exact sequences. So like a short exact sequence in the category of short exact sequences.
But so there's one thing. So length 2 chain complexes are not short exact sequences, right? Being exact imposes like an additional property. Does it not?
I thought the property is just that the
No, there's an additional thing. What is it? Short exact sequence. I always get confused about the same thing.
But my question, why can't you just go do one step more and then take like?
Yeah. So the point is that if you are a chain complex, the image of the left map is included in the kernel of the right one, whereas if you're exact, they're equal.
Okay.
But so this is slightly more specific. But sorry, what was the question?
Why can't you just say do this and then iterate it and then say take like a short exact sequence of these diagrams on top, like do it again? Like, have you thought about that?
I guess you could, but then the question is, what would would there still be a interesting interpretation for the resulting thing?
Yeah, I have no idea. You just do something almost the same thing twice. Yeah. Why not do it a third time?
Well, I guess you could, but you have to find out if it's actually useful or interesting.
Those are my own questions. Any more questions from the room? No. If not, let's thank Robert again.
Can I ask about you said that this cannot deal with the Almat and escape, like, but is it do we need this too? Because like the H gate can be just dealt with in the same code block. It does not need to have canonical block codes interact with stuff.
You're really fuzzy and I can't hear a lot of what you're saying. I think you were asking about Clifford circuits somehow, but I didn't get the end of the question.
Sorry, the door was open. I don't know. I was asking like, here says that it is not used Almat gates yet, but is that a problem because H only acts within one code block? So, what's the point of like why should like something like surgery also be able to deal with code Almat here?
So I mean, I have a couple of answers to that question. The first is that if all you are interested in is compiling single gates, even then there is no reason to sort of inherently treat any unitary different from any other unitary. The fact that we work with CNOTs here comes down to the fact that CNOTs are basically all we're able to do with CSS operations. But there's no reason why you shouldn't also be able to do H things in similar ways. Even if at the end of the day, you're doing something just local to one qubit, if you have one qubit encoded as part of many qubits in one big physical code, you still need to be able to address that individual qubit, and sometimes that's not trivial, even if at the logical level, the H is acting only on that one qubit. And then I think the second answer to the question, which is probably closer to my heart, is that for me, in the long term, I don't think that it is particularly sustainable to continue with the approach of compiling individual gates from a logical circuit into a fault-tolerant implementation one by one, because this incurs, I think, a lot of inefficiencies and you're losing a lot of optimization to the specific choice of logical circuit that you came up with. That doesn't really have any bearing on what the fault-tolerant implementation should be, other than that it has to implement the right unitary. And if we want to implement a circuit that contains more than just, say, one gate or one type of gates, CNOTs, H's, and S, then we still need a framework that's able to address all of these things at the same time. Does that make sense?
Yes, thanks.
When you say only CNOT, but that's anything you can build out of splits and merges. So you could also do like Pauli, 2-qubit Pauli measurements.
Sure.
Many qubit, yeah.
Yeah, so I guess you can do, if you allow yourself to do also somehow single qubit Clifford unitaries on auxiliary circuits, then you can do multi-qubit Pauli measurements, and that's quite a lot stronger than this. But I don't, at least off the top of my head, know how to do that.
Yeah. Okay.
Sorry, so I'm wondering, in order to investigate whether you have a fault-tolerant circuit, you still need to know how to implement your logical Clifford gates. Now, given this map between different vector spaces, how do you find the implementation of Hadamard, S, and Clifford and other Cliffords?
I mean, my hope is to be able to come up with properties that these maps need to verify in order for a fault-tolerant implementation to exist. I think that this is, I guess this is just a hunch at this point, that these kinds of things exist, but it's certainly not obvious. No, I don't think that it's like an easy question.
Thank you.
And on some level, maybe also the answer will just be algorithmic. Say, I give you a code, there's an algorithm that tries, and if it like comes up with a solution enough of the time, that's good enough for most of your applications. And I guess that gives you a practical, if maybe unsatisfying answer.